everyone. This is the Unit 4 take-home test video key. If we complete this, it's going to help us be prepared for our Unit 4 test that is coming up. So we're going to start at the very beginning, and it says horizontal rows on the periodic table are called periods. I like to tell everyone I remember this because it takes a long time for you during your day to walk from period to period, from class to class. That's the long way. Columns, on the other hand, those are not as long, and these are called groups or families. Elements in the same column have similar chemical properties. Because they have the same number of valence electrons. The next one says, list two elements with chemical properties similar to chlorine. Really, I can look at any of my halogens. Halogens are in that group 17 right here. They're this color, so I could pick any of those. I'm going to pick, let's see, bromine and fluorine. Alright, and I'm just going to do a couple of these next ones. It says, how many valence electrons do each of the following groups have? I'm going to pick halogens. We were just looking at those. That is 7. And I'll do alkaline earth metals. And those have 2. Okay, so back to our little colored sheet. I like to tell my students the difference between the alkali and alkaline earth. Alkali has one word, so that's the group 1. Alkaline earth, 2 words. Alkali earth, that's the group 2. Alright, and I think y'all can fill out those other ones. Now we're going to go down to this one, and it says, what oxidation number will the following groups have? And we're going to do the opposite. So we'll do our alkali, 1 word, oxidation number of 1, and then we'll also do, I think, the noble gases. And remember, the noble gases actually have an oxidation number of 0 because they already have a complete octet. Alright, for the next one, it's asking to draw Lewis dot structures. So for our Lewis dot structures, these are just the little pictures with the valence electrons only. So I'll do potassium because that one's easy. And potassium only has 1 valence electron, so I'm just going to give it 1 dot. And how about we do another halogen, chlorine. So I always told my students, when you're getting on a plane, your pilot and co-pilot always ride together, and then everyone else files in one at a time until they are forced to start sitting next to other people. It's going to look something like that. Okay, so I'm going to let you fill out the other ones, and I'm going to move down to this section here. And I'm going to say this will be our first place where we can get some extra credit. So go ahead and put a star on and write in oxidation numbers not same as valence electrons. Why I'm having you write that is because a lot of students are tempted to say that those are the same numbers, and they are not. So first we're going to write in our oxidation numbers. Okay, so our oxidation numbers are just the ones that you colored on this list. Y'all made this coloring from this sheet. And they are not the exact same thing as valence electrons. So that was our +1, +2, 0, and -1, -2, -3, -4. Okay, and then it says to shade in the metals that never require a Roman numeral when naming an ionic compound, and that is from our exception block. Okay, so all the other transition metals get a Roman numeral except for silver, zinc, aluminum, gallium, indium, cadmium. So it makes a lovely little staircase with the charge of +1, +2, and +3. Okay, and then it says to circle all the nonmetals. So I remember my nonmetals because I've been thinking about that staircase. So our staircase is what separates our metals from our nonmetals. So not very many things on the periodic table are actually nonmetals. Here they are. That's kind of a weird looking circle, but there they are. Everything else is a metal. The other thing I'm going to do is also shade in the area that is transition metal, and I would recommend this because remember our transition metals are the things that do need Roman numerals. So this entire section, all of these things need a Roman numeral. Except for our exception block. Okay. So that's that part. Now, moving on, I am going to answer all these questions because I think they are so important to doing well on this test. So, number 8 says, ionic or covalent. Which type of compound can require Roman numerals when naming? That is ionic. Sometimes, if it's in this green section up here, it will need a Roman numeral. Not always. If it's one of the exceptions or in our groups 1 or 2, no Roman numeral required. Which type of compound contains only nonmetals? That is a covalent compound. Covalent compounds are only nonmetals. Which type of compound may have a metal bonded to a polyatomic ion? That is an ionic. The key word to this is metal. Anytime you see a metal, you know you're not dealing with covalent compounds. Next one, ionic or covalent. Which type of compound conducts electricity in solution? That is going to be an ionic compound. A good way to remember that is that an ionic compound has a metal in it. So we know metals are conductors. So sometimes when they're in solution, they will make good conductors. Next one, which type of compound will share electrons in a bond? Will share. So for this one, I'm going to say sharing is caring for covalent. That is where we see the sharing. On the other hand, for 13, ionic compounds involve the transfer. Ionic compounds are the stealers. They are not nice. They transfer those electrons, they steal them away. And number 14, which type of compound uses prefixes? That is, of course, our covalent compounds. Unlike Roman numerals, covalent compounds always use a prefix. Always, always, always. Okay. Moving on. I'll do a few of these. It says, be careful, some are covalent, some are ionic, and some require Roman numerals. So the first thing I would do, if I was you, would be to highlight or write an I or a C. I'll write an I or a C, like I've been using, to first identify them. We can do the identification for all of them, and I'll name some of them. So the first thing you want to do is look at these problems and determine, does this have a metal in it? And you only have to look at the first one, because remember, as a naming convention, we always put our metals first. So if you see a metal in the first element, you know automatically this is going to be ionic. So I'm going to look at this, Mg, that is a metal. So I'm going to put a little I next to it. C is not a metal. Carbon is not a metal. Next one, iron, that is a metal. Another iron. Lead is a metal. S, sulfur is not a metal. I'm going to put a C right there. Nitrogen. Nitrogen is not a metal. I'm going to put a C. I just realized this C kind of looks like a G, but got this erasable pen, so I'm okay. All right, next one, aluminum. That is a metal. Phosphorus, that is a non-metal. Carbon is a non-metal. Lead is a metal. And phosphorus is another non-metal. So now that I have all those written out, it's going to make the naming much more simple because I'm not going to have to sit there and try and remember which naming system to use. Because we know there are two naming systems, Ionic, which is the more complicated one, and Covalent, which is easy. Okay, so this first one I'm going to work with you, and I'm going to try and write all my ionics in red and my covalents in blue to make it simpler. Okay, so the first thing I want to think about when I am naming my ionic compounds is that it is a 4-step process, but we want to always kind of start with a step 0 in that sometimes we need Roman numerals. So I want to look at magnesium and think to myself, does magnesium need a Roman numeral? And if it helps, you can look at this list. I see magnesium is right there. It does not need a Roman numeral, so I am safe. So I'm just going to write magnesium chloride. Remember, we always use that IDE ending, whether it is a ionic or a covalent. That is the ending unless it's a polyatomic ion. So on my next one, it's just covalent. We're safe. Covalents are easy. So I see that there's an subscript of 1, but you never, ever, ever write mono to begin with. Our covalents always use those prefixes, but we don't use mono for the first element, only the second element. So this is carbon. And then I see that there's a subscript of 3. So I'm going to put in my 3 subscript, oxide. Again, that IDE ending. All right. I'm going to skip, I'm going to skip this one, but I am going to do this one. This one is ionic, and so when we're thinking about this, remember it's a 4-step process, especially when we need a Roman numeral. Our step 0 is that it needs a Roman numeral because Fe is a transition metal. Transition metal anywhere in this orange section. Iron is right there. It needs a Roman numeral. We have to tell it what to do. All right, because it needs a Roman numeral, I'm always looking to the anion, in this case the oxygen, to determine what that Roman numeral is. There is no subscript. So whenever you see no subscripts, that's your little signal. You need to look a little closer and make sure, because you can't just make the assumption that they both must be 1, right? It could be that there's something else and then it is reduced down. And in this case, if I look for my oxygen oxidation number, it is 2. So that has to be what the iron is also charged. Because if you think about it, if this is 2 and oxygen is -2, when they swap and reduce down, that's what it would look like, your formula at the end. So I'm going to write it that way. Iron 2 oxide. Okay? Now, compared to this one's a little more challenging, because if we look at the one above, it's easy. We can just look at that anion, and it is iron, 3 oxide. Okay, so let's keep going. Let's do another covalent. We'll do this one. Okay, this again, understood 1, but we don't need to name mono at the beginning because mono never ever goes on the first element, only the second element. So that's going to be S. So we're going to name it sulfur. And how many are there? 2 dioxide. How about one where there are 2 monos? So you can see that mono does go in the front of the second element. So that's why I'm going to pick this one right here. So it is not monocarbon oxide, monoxide. It's, of course, no mono in the front. So we're just going to say carbon monoxide. No mono in the front. That's the point of that one. And let's do another covalent with a little bit more complicated prefixes. So here we have 6. This is phosphorus, and you just have to memorize your prefixes. So I'm going to say the prefix hexa, phosphorus, and then this next little prefix is the one that students tend to forget because it's a weird one, but 7, the prefix for that is hepta, but we don't put the A in with oxygen because A and O don't really work together. So we're going to say heptoxide. Heptoxide. Alright, and I'll do one more ionic one that has a polyatomic ion, so we can review how to name those. Alright, so the first thing I want to do is take a look, and my step 0, I want to think, does this need a Roman numeral? I know it's ionic, I already identified that, but then I want to think, does lead need a Roman numeral? So if we look at our sheet that we colored, yes. Lead does need a Roman numeral because it is not one of the exceptions and it's not one of the groups 1 or 2. So we're going to have to think about that. So first thing I'm going to do is write lead. I'm just going to put the parentheses in there to remind me that I need to go back and put a Roman numeral. But then I'm going to take a look at this SO4. Now, anytime you see a parentheses, that is your hint that you are dealing with a polyatomic ion. Thank goodness you don't have to memorize those. They are nice, just given right to you. So you just need to find the one that matches and copy that name exactly. That is sulfate. Okay, so I'm going to write that name exactly down as I see it. Sulfates. And this also tells me that the charge on sulfates is -2. So this is the part where it can be a little bit tricky because we also see that a 2 is over here. So that means our original formula, sulfate, we know for sure has a charge of -2. So we need to think about what could have possibly crisscrossed and reduced to leave a 2. So if this 2 in the original formula came over here and they were both 2, then our formula would have reduced down completely. But that's not what happens. So we have to think, what could we reduce by 2 and still end up with 2? And that is 4. Because if these crisscross, that 4 would be right here. They would both reduce. And that is what we saw in our formula. So we know it must be lead 4. I know those problems are hard. So we'll give you the next little bonus point for writing metals are messy. I would draw a little star by it so you can make sure your teacher sees it. Always helps me out. Okay. Next problem. We're going to do number 17. What is the name of Cl2O5? Again, the first thing you want to be thinking, is this ionic that I'm dealing with or covalent? I can just look at this first one. Chlorine is a nonmetal, so therefore I must be dealing with a covalent compound. Covalent compounds are easy. You can do them quickly. So I only need a prefix. I don't have to worry about crisscrossing, swapping, dropping, none of that. Okay, and if it helps, use your foldable. Okay, I love this. It's very helpful. Cl2, so I know it must be dichlorine, and then I'm looking for 5, pentoxide. I can eliminate anything with a Roman numeral right from the beginning. So we know it has to be that answer. It's the only one that has a prefix. All right, so how about number 18? Again, the first place you should always look is that first thing that I'm dealing with a metal. In this case, yes. Then I want to be thinking more specifically, what kind of a metal? Copper is, of course, a transition metal, so it needs a Roman numeral. So if I'm writing that out, this one is easy because I can just look at the anion to figure out what the Roman numeral is. Never, ever, ever use the cation, this subscript here, as your Roman numeral because it's a swap. Always take it from the back. Take it from the second one. So if I'm looking at that, I'm going to be looking for the 2. So it's going to be copper 2 nitride. Don't make the mistake of choosing the anion. Don't do that. Definitely don't make the mistake of using prefixes anytime you have a metal in the front. Prefixes are only for nonmetals. Okay, now let's practice some formula writing. Again, I find that this is very helpful. Use this foldable. It's a great tool to help you learn. All right, so I'm going to do a little mix of ionic and covalent. This one I'm going to do, this is Cobalt 3 sulfide. Right away I notice that cobalt is a metal, and I also see this Roman numeral. So I know this is an ionic compound. So ionic compound means 4-step formula. 4-step formula. So we'll give you another +1 there. 4-step formula. Right, ionic, 4-step formula. Okay. So this is not a Roman numeral 1, by the way. That is an I for ionic. So step 1, you're going to write out your symbols. My symbol for cobalt is CO, and my symbol for sulfide is not polyatomic. I know that because of the IED ending. So I'm going to write an S. Now I'm going to fill in step 2, which is charges. The charge on cobalt, a lot of times students are like, I don't understand, I don't know how to find the Roman numeral or the charge for a transition metal. And I say, yes, you do. That's the whole point of our Roman numerals. That's what they're there for. It makes your life easy. So I know it is +3 because that's Roman numeral 3. Then I just have to think about the charge on sulfur, which is -2. Don't just leave them there. You have to swap and drop or crisscross, whatever you like to say. So this 2 comes over here, and that 3 goes over there, and then I'm done. It does not need to be reduced. All right, so now let's do a covalent one. This one's covalent. I see a prefix, so I know it must be covalent. Covalent are easy. We love those. Pentasulfur. So penta, I know that's the prefix 4,5, so I'm going to write S5, and then it says tribromide. So I'm going to write Br3. And that's it. No swapping, no dropping, no crisscrossing, reducing, erasing, none of that. What you see is what you get. So very easy. We love those. And that doesn't really look like a Br3, but I'll try and write it a little more clearly. There we go. Alright, next one. This one is Ionic. So that means we have to do our 4-step formula. Step 1, or really we want to think about our step 0. Remember, this is something that has a Roman numeral, so we're going to keep that in mind. So we're going to turn it into symbols. Iron is Fe. That IDE ending tells me it is not polyatomic, so I'm going to write O. Step 2, we're going to write in our charges. Remember, I know this charge because it's telling me. Okay, so +2. The oxygen is -2. They crisscross. And then our last step, these reduce. So it is just FeO. Don't forget to reduce. We don't need to reduce for covalent compounds, but you have to reduce for ionic compounds. Alright, and let's do one more that includes a polyatomic ion, just so we're fresh on those. So I'm going to do this one. This is Ionic. Okay, so 4-step formula, I know it's Ionic. Step 1, symbols. Symbol for barium is Ba. And then I see chlorate, ATE. So that is not an IDE ending. So that is my signal. I need to go check on my polyatomic list. And I'm looking for chlorate, and then I'm going to copy down exactly what I see. So chlorate is ClO3. And now we'll fill in our charges. Barium has a charge of +2. Chlorate has a charge of -1. So they are going to swap. That 1 is going to come over here. That 2 is going to go over there. And then we can erase that 1 if you want to. Get rid of that. So I'm going to circle that so it's out of the way. So that's it. And then I think you can do the other ones on your own. Alright, so let's do number 20. It says, what is the formula of tin 4 sulfites? So this one's a little complicated because I have a Roman numeral and I have a polyatomic ion. I know it's a polyatomic ion because of this ITE. So 4-step formula, I'm going to write this out. Tin, I'm going to first translate. Tin is SN. And then I want to figure out what sulfite is. We don't have to memorize that. It's on our list. Here it is, sulfite. That's SO3 with a charge of -2. My charge on that tin is 4, so +4. And then, of course, we have to crisscross. Do not forget to crisscross. Okay, crisscross. That 4 comes over here. That 2 goes over there. And our final step is to reduce. That reduces down to 1. And that reduces down to 2. So it's going to be the final part is SnS2. Alright, let's do the next one. Thank goodness, it is covalent. That's so much easier. Tetranitrogen decachloride, I just write what you see is what you get. What you see is what you get. So I have tetra, meaning 4, and deca, meaning 10. So that's all I have to do. Tetra means 4, deca means 10. That's it. Okay. I think we're good for this page. All right. Well, what the heck? We'll do one more. We'll do 23. Strontium phosphide. So for this, you want to first identify, again, is it ionic or is it covalent? You take a look at the periodic table. Strontium is Sr. That is a metal. So it is an ionic compound. All right, so step 1. 4-step formula. Step 1, we're going to write out the symbols. The symbol for strontium is Sr. We see that IDE ending, so we know it is not polyatomic. So instantly you can cross those out because they are polyatomic, and our IDE ending means it's not polyatomic. So then we're going to write in our P for phosphorus, and then we're going to add in our charges. My charge for strontium is +2. My charge for phosphorus is -3. Don't just leave them up there. They want to crisscross, jump. 3 and 2. So which one matches that? It's C. All right. Next page. Oh, I have another formula to do. Iron 3 oxide. This is a good one. Okay, 4-step formula again. Iron is a metal. This is an ionic compound. So my step 1, symbol. Now my charges. Don't forget, you know what that charge is because that's what the Roman numeral is telling you. Oxygen is -2. They crisscross. And that's what you get. Okay, so now I'm going to start filling these in with my word bank. It says blank bonds occur between 2 nonmetals. And that is a covalent bond, of course. If you are like me and you sometimes forget, I told my students the first 2 letters in covalent are C and O. That makes me think of carbon and oxygen. So those are both 2 nonmetals. That might help you remember. So we'll give you +1 for that. Okay. In this type of bond, electrons are shared. Sharing is caring with a covalent bond. I was about to write sharing. Shared. Blank bonds form between a... Okay, so blank bonds, that's going to be ionic bonds. A metal and a nonmetal. In this type of bond, electrons are transferred. All right. And 27 is kind of the same, but we'll do 28. Electrons dissociate to form a sea of electrons in this type of bond. That's a metallic bond. We didn't talk about that a lot, but what you want to be thinking about is that word sea of electrons. That has to be a metallic bond. Which of the following sets of atoms will share? Okay, so share, we really want to be thinking immediately. Sharing is caring. That is a covalent bond. So if you see a metal, just cross that off. All those are metals. Take out that garbage. Okay? Now we're doing the opposite on this one. Keyword being transfer. So we want to be thinking about metals only. So if you see two nonmetals like this, I'm going to cross those off. Okay, and that leaves me with only this one because sodium is a metal. Alright, so I'm going to draw some structures. Here is H with its one sad, lonely electron, and then fluorine, which has another lone pair electron. And these form a nice linear bond. Remember, your key here is that linear, you have 2 to 3 bonded elements. So 1, 2 that are bonded together. So how about this next one? It says CH4. So I have 5 total, because there's an understood 1. 1 plus 4 is equal to 5. So I know automatically that has to be tetrahedral, because that's the only shape that has 5 total bonded elements. So I'm going to write that in there, but I'm also going to draw it for you. Tetrahedral. C, H, H, H. Okay. Good way to remember these kind of, in my mind, is that they sort of look like, if you drew lines connecting it, it would sort of look like a square, like invisible lines. Unlike trigonal planar, which if you drew invisible lines on a trigonal planar, it would not look that way. It would look more like a triangle. So here's a trigonal planar. Boron's usually in the middle of a trigonal planar because boron's a moron, and boron only wants 6 valence electrons instead of 8 like everybody else. So B, F, F, F. See how it looks more like a triangle if you were to connect the lines like that. It looks like a triangle. And I can count 1, 2, 3, 4 bonded elements, so it must be trigonal planar. Alright, which of the following would be considered a tetrahedral molecule? Again, I'm looking for 5 bonded elements, 1, 2, 3, 4, 5, and kind of would look like a square if I drew the lines around it. That one. Moving on. Okay, label the following ionic or covalent. I'm just going to do a couple of these because these should be really easy right now. You're just looking versus nonmetal. Okay, is hydrogen a metal? No, that's covalent. Is carbon a metal? Nope, that's covalent. Remember, you only have to look at the first one to know. Sodium is a metal. That is ionic. Magnesium is a metal. That is ionic. I'll let you do the rest of those. Word bank. Here we go. Compounds with boron in the middle. Remember, boron's a boron. That's going to be trigonal planar. In fact, let's make that our bonus. +1. Boron, the moron. Okay, compounds with carbon or silicon in the middle have what type of shape? Usually tetrahedral. Compounds with 3 bonded atoms, again, that's the trigonal planar. And I'll let you answer the next couple of ones there. And on this one it says name the shape. I'm gonna do this one because we haven't had one like this yet. Even though there are 3 bonds altogether, it is a triple bond. The name of the shape is actually linear because there are only 1, 2 bonded elements. Remember, 2 to 3 bonded elements are always going to be linear, 2 to 3. Okay, so there are only 2 elements. I'm not looking at the valence electrons, not worried about that. I'm looking at the actual elements. There are 2 of them. That's a linear shape. Okay, more shapes. Let's see, here's a good example of a linear. Even though I see some double bonds, I still only have 3 total elements. Remember, linear can be 2 or 3. So this one's linear. All right. A few more that we'll answer on this page. The mass of 1 mole of a substance, the mass of 1 mole is going to be the molar mass. So when we're asking about molar mass problems, that is not this number here, okay? Molar mass, if you see the word mass in there with the units gram per mole, that's when you're looking at the periodic table at the average atomic mass. This, on the other hand, 1 mole is always this number. So 1 mole is always 6.02 times 10 to the 23rd. Always, always, always. Okay, and percent by mass of each element in a compound, that is percent composition. Oh, and I just realized actually 6.02 could also be Avogadro's number. These could both be the same, right? 50 and 51 could both be C or A, because Avogadro's number and a mole are the same thing. Okay, how many atoms are in 1 mole? It's not asking me molar mass, so 1 mole must be that. Contrasted to molar mass, when you see the word mass, you need to be thinking about the periodic table. So you need to find nickel. Nickel is a transition metal. It is right there. And you're going to take that number, the average atomic mass, and copy it exactly. So that is choice C. So I'm going to do a couple of these analogies. These are fair game on a test. You can have an analogy problem like this on the test. Okay, so gram is to mass as mole is to, what do we think? A mole is to the amount of a substance. Just like gram is a way of describing mass, mole is just a way of talking about the amount in a substance. Okay? Unlike this one where it says grams to mole is molar mass. Okay, so a couple more. I have to wrap up. The bell is about to ring. Oh, we're going to pause and come back. Okay, so for this first problem, it says find the molar mass of Fe2CO3, and there's a little subscript 3. The first thing you want to do is take that subscript and you need to distribute. Remember, it goes, if it's outside of the parentheses, it needs to go to everywhere inside of the parentheses, but the parentheses is like a wall. After that, it stops. So this 3 distributes to the oxygen and to also the carbon. So to find the molar mass, we need to use all those subscripts, multiply by the subscripts, and add the whole thing together. So we've got Fe, we have 2 of those, right from the formula. We're going to multiply by the average atomic mass. I'm going to get this straight from the periodic table. I'm going to find iron. It's right there. I'm going to copy that down. I think it says 56. Or is that 50? Yeah. Is that 55 or 56? 55. 55 times 0.845 plus, okay, now I'm going to do C. There are 3 of them. And the mass of the carbon is 12.011. And then I'm going to do the oxygen. There are 9 of them because we said 3 times 3 because of that parenthesis distributing. So there is 9 times 15.999. So you have to do it with the parentheses, otherwise your math is going to come out wrong. But if you take your calculator and you plug it in like that, you're going to say 2, oops, I didn't do my parentheses right, 2 times 55.845, close, plus 3 times 12.011 plus 9 times 15.999, and that's what I came up with. So I'm going to write that in there. Alright, so now I'm going to work this problem 59 where it says nickel 2 nitrates. So the first thing I need to do is think about my formula. Remember, it is a 4-step formula, Alright, first step, I need to write out my symbols. My symbol for nickel is Ni. My symbol for nitrates, what do I notice about nitrate? It ends in ATE. That ATE ending means I need to look right over here. And then I'm going to copy it exactly like it says. So it says NO3. Step 2 in my 4-step formula. Step 2. I'm going to add in my charges. You might say, Ms. Stafford, I have no idea what nickel is. It's a transition metal. I don't know what to do about that. I'm going to say, yes, you do, because look right here. It's nickel 2. That's what that 2 is telling you. That's the charge. Okay? The charge on that nickel is plus 2. Now, for nitrate, you don't have to have that memorized either. It's on your polyatomic sheet. So I'm going to find nitrate, and the charge on that is minus 1. Of course, we always, every single time, no exceptions, crisscross. So that 1 for the nickel is going to come over here. The 2 is going to come over to the nitrate. And that is my formula. It is Ni, NO3, 2. Now, we still have to find the molar mass. And we're going to do just like we did up on this problem to find the molar mass. Take it one step at a time. I have to first distribute what's inside this parentheses. So this 2 is going to come over here. It is also going to go over to the nitrogen. It is not going to go to the nickel. So for nickel, I just need to find nickel on the periodic table, write that down. So nickel is, oh, this periodic table is so hard to read. 58.693, and that's straight from the periodic table. And then I'm going to add that to 2 nitrogens, which is 2 times, because that 2 distributes, the mass of nitrogen, which is 14.007. And now I have to finish it off with oxygen. There are 3 of them. Or, oh no, I distributed that wrong. There are 3 of them, but that 2 distributes, so there's actually 6 of them. We're going to say 2 times 3 is 6. There are 6 of them, times the weight of oxygen, which is 15.999. And again, I'm going to put all that in my calculator, but I'm going to do these one step at a time because we want the parts. So our part for nickel is 58.693. Our part for nitrogen I'm going to say 2 times 14.007. That is 28.014. And then I want my part for oxygen, which is going to be 6 times 15.999, which is 95.994. Then you want to add all of these numbers together. Okay? So I'm going to add them all together. I'm going to take that 99 or 95.994 plus nickel, which was 58.693, plus nitrogen, which is 28.014, and that is equal to our molar mass. This is our molar mass. It is 182.701. Now, for percent composition, you want to think to yourself, part divided by whole times 100. And that's why I broke it up into these steps, because we needed the parts. Okay? Okay, so for our percent composition for nickel, again, we wanted our parts. We're going to say 58.693 divided by our total, which we got right there. That's the molar mass, times 100. That's a weird looking time sign. Okay, so when you plug that in, in this particular compound, the percent composition of nitrogen is 32.125. So I'm going to write that right here. That's our percent. And then we can do the exact same thing for, I'm sorry, that was nickel. Now we'll do the exact same thing for nitrogen. So we're going to take that part. Here's our part. .014 divided by whole. Again, this number up here is your whole. That 182.701 times 100. So let's plug it in. So you get 15.33%. And then let's finish it off. Oxygen. So part divided by whole times 100. Here's our part. 95.994 divided by 182.701 times 100. Plug it in. So I'm going to delete that. All right, so that is 52.54%. So if you're wanting to check your work on these ones, what you want to do is see if all of your percentages add up to 100. So I want this 52.54, 15.33, and 32.125 to basically add up to 100, and that way you can check and make sure you did it correctly. So I'm going to check and see. I have this one already in the calculator, and then I'm going to plug in 15.33 plus 2.125. And I got really close to 100, right? So I know I did it correctly. So I'm good. And that is so complicated. So you can write this on the bottom of your page, and it is plus 1 bonus, right? I am tired. Alright, so they are not always going to be that hard. Okay, sometimes we just straight up give you the molar mass, and that helps a lot. Like in this problem, we give you the molar mass, so we have that already added up, but at least now you have a place to start. Do you want to do one more of these problems? Yes? Alright, let's do another one. So here's our molar mass, and here's our formula. So we know this is what the total is, but we still have to figure out the part. Because remember, our formula is part divided by whole times 100. So in order to figure out the parts, we have mg. There's only one of those because this is not distributing. So we're just going to write down the molar mass of mg. So you're going to need your periodic table. You're going to get that out, take a look, find mg, and write down the molar mass. So mg is 24.305. So I'm going to write that down. Remember, it's part divided by whole times 100. So my part is 24 mg. 24.305 divided by whole. That's right here. We did that for you in this one. Times 100. So let's plug that into our calculator. 24.305 divided by 58.319 times 100. Syntax error. Let's see. Don't do what I just did. There we go. 41.676. Alright, let's keep going now. Let's do O, because we actually don't know the part of O, because there are how many O's? There are 2 of them, because that 2 distributes. So we have to say O, we're going to say 2 times 15.999, which is equal to 31.998. And now we're ready to do our percent composition for that. So we're going to say parts divided by whole from right here. So there's my part divided by whole times 100. Okay, so that is 54.867. And now last we need hydrogen. And we have 2 hydrogens, we know, because this 2 distributed. So hydrogen, we're going to say the weight of hydrogen, which is 1.008 times 2. .016. So that is our parts divided by whole, which is 58.319 times 100. Okay, so there it is. 58.319 times 100. And that is 3.45. I'm going to round that to 7. And now we can check our work and make sure we did it correctly. So I'm going to add them all together. all my parts and see if they're close to 100%. Hopefully they are. 54.867 plus. Yes, I got a number very close to 100. So I know I did it correctly. So that's all good. So that is how we can do our percent composition. Again, maybe we'll make this plus another one because I am tired. That was a lot of work. And I think y'all can probably do the last couple by yourself because they are simpler. And so that's going to be the end.